Hello, everyone. Welcome to the London Machine Learning Meetup. I'm Giuseppe from Evolution AI, and I'd like to welcome Tim Dettmers from the University of Washington, who's going to talk to us about QLoRA, and Nick Guha, who from the University of Stanford, who is going to moderate the discussion. Just a couple of quick technical details before we start. So as usual, please ask your questions using the Q&A tool. You can ask your questions as we go along during the talk, and we'll read them out during the Q&A session. If you would like to ask your question yourself, you can raise your hand and we'll unmute you so that you can ask your question and basically have a short discussion with Tim. If you have any technical issues or something, you can use the chat to chat to us. And a couple of reminders before we start. The talk is going to be recorded and it's going to be available on our YouTube channel. So please follow us on YouTube if you want to stay up to date with the latest videos. And also the next meetup is going to be a bit earlier than usual. So it's going to be probably in a couple of weeks. So stay tuned for the updates. Okay, welcome again to Tim and Neil. I leave it to you for the talk. Enjoy the talk.
Yeah, thank you so much. Yeah, so today I talk about QLoRA, efficient fine-tuning of quantized LLMs. And if we look at language models that are available today, maybe I should have put LLaMA 2 on this slide, which is a little bit larger, the largest model, 70 billion parameters, but they use quite a bit of GPU memory to be run or to be fine-tuned. And what I do in my work is trying to make large language models as efficient as possible, and particularly making them more accessible. And so I developed different techniques, SPQRs for very efficient sort of inference. Today I'm not going to talk about this, but we're going to talk about QLoRA, which is a method that reduces the memory footprint for fine-tuning of these large language models by a factor of 17. And then you can fit the large language models on a single GPU. So consumer GPUs have 24 gigabytes, so LLaMA 33 billion model, also the LLaMA 34 billion model, the LLaMA 2 34 billion model fits on a single consumer GPU. And if you have two consumer GPUs or a sort of a low-grade data center GPU with 48 gigabytes, that fits also into one GPU and makes fine-tuning much more easy. One thing is also fine-tuning requires a lot of memory, but usually not that much compute. So usually you just need to fine tune for a day or less than a day, sometimes even just a couple of hours. But fitting these models into a GPU is quite difficult. And so in this talk, I talk mostly about QLoRA, but there's sort of a little bit of literature that I will talk about that is sort of background for QLoRA. In particular, the K-bit inference scaling law paper, and has very important insights that basically was the foundation of QLoRA. Basically, we took all the insights from that paper and developed a fine-tuning technique. And so I will talk a little bit about that in the background, and then also a little bit of my other papers and how they tie in with QLoRA. Yeah, so before we dive into sort of these papers, in particular QLoRA, I will give you a little bit of background. So my work is mostly about quantization. And so quantization is if you have a continuous signal and you want to discretize it or digitalize it. And that means you need to bin the continuous signal into some discrete bins. In computer science, quantization is also when you have a data type with more bits, and you want to bin it basically or quantize it into a data type with less bits. And if we have integer quantization, this is very similar to histogram binning. So here in red, we have a normal distribution, and in blue, we have a histogram. And this histogram has 16 different bins. 16 bins would be equivalent to a 4-bit integer quantization. And so what we basically do in integer quantization is we find the range of the distribution, so the minimum, the maximum, and which is about -3 to 3. And then we slice this interval in equal width slices. Then we take all the numbers contained in the slice and quantize it to the middle value of this bin. And what we get with that is 16 different values that represent the entire normal distribution. And that's how we do 4-bit integer quantization. If we want to generalize it sort of a little bit to other data types, we need to think a bit more broadly. So the difference, for example, between integer data type and a floating point data type is that they have a different range. And so to bring them into the same range, we can normalize both these data types so they have the same range. And an easy way to do this is divide by the absolute maximum value of each of these data types. That will normalize it into the range of -1, 1. And in my work, I usually use this kind of normalization just to basically have all data types to be in the same range so you can handle it in the same manner. That looks like this. If we want to do a quantization itself, it's sort of a two-step program. The first is we normalize an input tensor into the range of the data type, which is usually -1, 1. So we can use the same procedure. We find the absolute maximum value of the input tensor x and divide by it. And then the input tensor is normalized into the range -1, 1. And then we find the closest value of each element that is closest to the value in the data type. And for integers, that's basically rounding. We find the closest integer in the integer data type. But if we have this more general representation, we do a binary search to find the closest element. And just to give you sort of an example what this looks like, here we have a strange 2-bit data type. And so we have an index and a maps to the data type values -1.0, 0.3, 0.5, and 1.0. So this is a data type with just one negative value. And then we have an example input tensor 10, -3, 5, 4. And so the first step is we divide by the absolute maximum, divide by 10. And then is we find the closest value in the data type, in the value map of the data type. And then we have basically these values are represented by the integer of the data type map. And this represents the quantized data, and we can store it. So we basically store the indices that map to the values in the data type. And if we want to undo everything, if we want to dequantize this quantization, we just reverse all steps. So we load the index from storage, and then we do a lookup where we look up just the values associated with these indices. And after that, we denormalize by multiplying by the absolute maximum value. And so the input was 10, -3, 5, 4. And the outputs are then, if we quantize and dequantize them, 10, 3, 5, 5. And so you see here, we made one big error. The -3 turned into a 3. And this shows that this data type is not suitable for this input data. And that in general is sort of a very important theme. If you want to have high precision quantization, you need to design a data type that is good for your problem. And I give you an example from one data type that I designed. And this data type was particularly good for 8-bit optimizers. So if you have atom optimizers, it's a ratio between the first optimizer state and the second. The first is representing the mean, the smooth mean over time, the other, the smooth standard deviation over time. And if you divide by a ratio, you can have very large numbers or very small numbers. So it's important to have a data type that can represent these values with high precision. And so to do that, I developed a dynamic exponent quantization data type. And it works like this. So we have an 8-bit data type. The first bit is reserved for a sign. Then the first 0 bits, a number of 0 bits, encode an exponent that is 10 to the minus the number of 0 bits that you have. Then the first bit that is 1 is an indicator bit. This indicator bit just indicates that all following bits are reserved for the fraction. And so as you slide the indicator bit from left to right, you can determine how large is your exponent and how large is your fraction of your data type. And with that, you can represent very, very small values if your exponent is very large, or you can represent very large values with high precision if your fraction is very large. And so with this, we have a good data type for sort of these extremes, but it also means that everything in between has lower precision. So this, for intermediately sized numbers, this data type has lower precision than, for example, a floating data type. So depending on what problem you face, certain data types are better than others. And it's sort of important to think about what is important for your problem. That was sort of data types. And another important sort of concept is outliers. If you're in engineering disciplines, what people often do is, if they do quantization, is they found outliers and they just say, oh, this is a value I don't like, I will just remove it. It destroys my quantization, and then they're good. And deep learning, you can't do that. In deep learning, outliers are usually very important. If you remove them, your neural network doesn't perform well. Outliers usually mean this is an important value. Please consider it carefully. And so just to show you what an outlier can do is represented here. Here we have, again, sort of a normal distribution, but now we have an outlier at -10. And so what you see now is that the bins between -10 and -3 are completely empty. There's just one bin with a single value at -10, and all the other values, bins have no value. And so how you can think about this is, if half of the bins are empty in your data type, you basically have a data type that has one bit less, because all half of the combinations are basically unused. And so to get a good quantization performance, it's important to utilize all bins quite well. And if you have outliers, this is a big problem, because then you might waste a lot of sort of bins that are empty. And so an important method that can take care of outliers is block-wise quantization, or also group-wise quantization called. And it works like this. If you have an input tensor, it can be some hidden state, it can be a weight tensor. You slice it up into small segments or small blocks of a certain size, and then you quantize each of these blocks independently. Now, if you have a big outlier, then only one block will be affected. For example, here I have a tensor and I slice it into 9 pieces. I have 9 quantizations. And on the top left, we have a block with an outlier, and there some bins are wasted. So you lose some information there. And the other blocks are just fine. We don't have outliers. And so there the bins are optimally used. So you use all the bits in your data type. And if we do this, we can still have the outliers and represent them with high precision. But at the same time, most bins will still be fulfilled, and the data type is used optimally. And so this is an important technique to take care of outliers. And with this, we come to a bit more complicated topics. And so this is taken from k-bit inference scaling laws. And k-bit inference scaling laws sort of answer the question, what combination of quantization parameters allows you to have each single bit the most information possible? So if you look at model quality, how can you ensure that each bit gives you the most quality? Another way to phrase it is, if you, for example, have a 10 billion model in 8-bit and a 20 billion parameter model in 4-bit, these models have equal amount of bits. Which model does better? And here I have a graph that sort of shows, this is a key result from the paper. On the x-axis, we have the total model bits. So how many bits are in the model weights. And on the y-axis, we have mean zero-shot accuracy. So we ask the model a couple of questions, and based on what the accuracy is in the response, it scores well or not well. And then in different colors, we have different bit precisions for the weights. Now what we see is, if we go from 16 to 8 to 4-bit, the average performance increases. That means each bit is worth more if we have less bit precision for each parameter. And we also see at 3 bits, things degrade. And the line is actually quite jagged. And these jagged sort of points are instabilities. That means our quantization is unstable and it doesn't perform well. And so what this graph basically says is 4-bit is pretty much optimal. And the answer is, if you want to get the best performance for a model, you should use 4-bit parameters for inference and as many parameters as you can fit on your device. And that gives you the highest performance. There are ways where you can do a little bit better, but then you need to consider both the inputs and the weights and then do a quantization. If you just look at the weights, it's very difficult to do better than 4-bit. There are some factors that influence performance beyond this. They have a tiny effect, but still a significant effect. And so I talked about block size, where you sort of slice a weight tensor into independent blocks, and then you quantize each of these blocks independently, effective against outliers. And so we tested a lot of different variables and looked at what improves this bit efficiency, what improves k-bits inference scaling loss. And so what we find is block size is one of the few things that improves performance. So if your block size is smaller, you do better. The other thing is, if you have a small block size, it can actually have quite some big memory footprint. So with each block, you have an absolute maximum value. If you store this absolute maximum value in 32 bits and you have a block size of 64, then on average, you add 0.5 bits per element in your quantization. And so this means that the blue line in this plot is not a 4-bit quantization. On average, it's a 4.5-bit quantization. And so we see from this plot basically 4.5 bit if you allocate 0.5 bit for the block size. And for a small block size, does better than having sort of larger blocks. And we find sort of similar improvement, or one of the few others that improves performance are data types. So I talked about the dynamic exponent and sort of integer quantization. These do less well. If you have a floating point quantization, these do quite well. Then there's also quantile quantization, a data type that developed that is information theoretically optimal, that also does very well. But yeah, the other takeaway is, so 4-bit is important, and the data type is important, and the block size. And with that, we have sort of the background. Now we talk about QLoRA. And so QLoRA is about fine-tuning. Fine-tuning is expensive. So if we break down the cost, this is like a typical cost of a 16-bit fine-tuning run. So there you have 2 bytes, and we look at the cost per parameter. So per parameter, the costs are 2 byte for a weight, 2 byte for a weight gradient, and 8 byte for the optimizer states, which is usually Atom and 32-bit. So in total, that's 12-bit per parameter. And if you do the calculation, a 65 billion model will use 780 gigabytes of GPU memory. That's if you have low-grade data center GPUs, that's 17 GPUs, or 34 consumer GPUs. So pretty infeasible to run. Now there is parameter-efficient fine-tuning, particular low-rank adapters. And these reduce the memory footprint by only learning a small amount of parameters. And if we do this, then the weights are still in 2 byte or 16-bit. But the other sort of the weights optimizer states, the weight gradients optimizer states, and the adapter weights, they consume relatively little, less than a bit. And in total, that's 17.6 bits per parameter. And if you do the calculation, it ends up at 140 gigabytes. So you need 4 data center GPUs or 8 consumer GPUs to fine-tune a big model. And so that is still very expensive. And so our innovation is QLoRA, where we quantize the base model in 4 bits. And so the base model is frozen. And then you have the low-rank adapters on top, which are learned. And these adapters are on 16-bit, but they're very tiny, so they consume very little memory. And so basically how it works is you put a mini batch through the adapters in the frozen model, and then you backpropagate through the frozen model into the adapters and update them. And so the base model stays frozen, the adapters are adapted, and that's how you learn. And so if you do this, the overall memory footprint shrinks to 42 gigabytes. And that is a single data center GPU or 2 consumer GPUs. So on 2 consumer GPUs, you can now fine-tune a 65 billion model. Another innovation that is shown here on the plot is page optimizers. And so page optimizers take care of the optimizer states, and they keep them on the CPU rather than on the GPU. And they're swapped into the GPU just when they're needed. To give you a little bit more details, it's sort of efficient if the optimizer states are always on the CPU. And so what we do with page optimizers is we have a lazy offloading algorithm where basically if you encounter a memory spike and the GPU would usually go out of memory, instead, basically an engine says, hey, I'm out of memory, please go, the optimizer says, please go to the CPU. And so it's evicted to the CPU, more memory, GPU memory is freed up, and the processing can continue. And this is often what you encounter if you have a large mini batch. So not all mini batches have the same size, the same length. And if you encounter one with a large sequence length, then the optimizer stays evicted to the CPU. And if you do the optimizer update after the mini batch processing is completed, then the optimizer state is back swapped to the GPU and processing continues. And if your next mini batch fits fully into the GPU, the optimizer state stays on the GPU. So this is a very efficient method of preventing memory spikes from crashing your training run, while also saving memory and not slowing you down very much because this offloading is pretty rare. So QLoRA has a couple of innovations, and one innovation that is a little bit silly but was quite important to fit it on consumer GPUs was double quantization. Double quantization is basically, as the name implies, the quantization of the quantization. And so if we quantize a weight, we have the quantized weights themselves, but then also the absolute maximum constants. And as I said, they can take up quite some bits. So on average, 0.5 bits. But what we can do is we can take these absolute maximum quantization constants and just quantize them again. And then we turn the 0.5 bits to 0.125 bits. And with that, we basically save 0.4 bits or 10% of the overall memory footprint. And this is important to fit it on a consumer GPU. Then the last innovation is a new data type. And this data type is information theoretically optimal for normal distributions. And so in the beginning, we looked at integer quantization, where each slice, each bin has equal width. And what this data type does, it allocates equal area to each slice. And so the area is equivalent to how many numbers are in each slice. And so that means if you have equal area for each bin, then equal amount of values are in each bin. And that means each bin is equally well utilized. There's no waste. So if the incoming number, random incoming number is quantized, you cannot predict in which bin it will be. It's equally likely that it will be in any of these bins. That makes it information theoretically optimal. And so this data type is constructed through quantiles. So you do sort of equal probability distribution. You have like probability with equal spaces. You find the quantile or the z-score, concatenate everything with a 0, so you can represent 0 well. And then you normalize it again to the -1, 1 range. And this is a normal float data type, or a 4-bit normal float data type, for short, NF4. And this is basically the recipe that we use for QLoRA. So very memory efficient, but then we also have this data type that gives you better performance. Beyond that, there's sort of a little bit more that we needed to do to get it to work. And one important thing is that also a lot of people always ask me is they're always skeptical if lower rank adapters are as good as normal fine-tuning. And so to answer this question, we took a baseline, really optimized the hell out of it. So it's really strong. And that's Alpaca hours, that's in 16-bit. And while this sort of chart shows 4-bit versus 16-bit results, the results are basically the same for 16-bit LoRa adapters, LoRa fine-tuning. Here on this chart, we have like different positions for the LoRa adapters. LoRa just on the attention layers on the feed-forward network, or both on the attention and feed-forward network layers. On the y-axis, we have Rouge L, which is often used to sort of compare how well a model summarizes certain passages. We use it to measure how well does it basically replicate the outputs from instructions in instruction fine-tuning of large language models. And this is, I think it was a 7 billion LLaMA model that we fine-tuned. And so what we see here in this plot is that if we just put low-rank adapters on the attention layers, we get poor performance. We cannot get quite to the baseline that we created that's sort of very strong, very powerful. If we put it on the feed-forward network, performance improves, but we're still not at the 16-bit level. And if we put low-rank adapters both on attention and feed-forward networks, then we get 16-bit performance. We get even a little bit above 16-bit performance. And so this was a very important insight. If you want to replicate full fine-tuning, you need to put low-rank adapters on all layers. And that was sort of an important initial point. And from then, it was a question, okay, now we can sort of replicate it in 16-bit, but does 4-bit quantization work? Does it do great performance? And so the first step was just to verify that our new data type is actually beneficial. And so here I have, again, these plots from k-bit inference scaling laws. And there you see in blue the float data type. And then in orange and green the normal float data type, and then the normal float data type with double quantization. And we see the normal float data type is much better. So it shows that, yeah, this data type is better. On the right, on the left, we show it just for LLaMA models, different LLaMA models, up to 65 billion parameters. On the right, we show it for many different models. That's OPT, Bloom, LLaMA, and then Pythia or NeoX. And what we see is there's a gap between integer and float. So float is better than integer, but then normal float is again much better than float data types. Measured in perplexity, so LoRa is better here. And so this shows the normal float data type is very strong. It performs better for inference. Now the question is, does it perform better for fine-tuning? And these are a lot of numbers. The important is the last column, the mean of all runs. Here we have instruction fine-tuning of differently sized LLaMA models on 2 different data sets, of the alpaca data set and the FLAN version 2 instruction fine-tuning data set. And we compare 16-bit versus 4-bit floating point versus 4-bit normal float. And so what we see from the mean is that if you use normal float and double quantization, we can replicate the 16-bit performance. But if you use just a floating point, we don't quite get there. So this shows that the normal float is actually important to replicate 16-bit performance. But we show we do replicate 16-bit performance, and that opens up this possibilities to do so many fine-tuning runs. So to compare to other papers do maybe 5 fine-tuning runs, 10 fine-tuning runs. In this paper, we do 1,000. And this is so because our method is so cheap, it's so efficient to run. And so once we have shown here that we get the same performance as 16 bits, what we did is we did a very, very broad exploration of instruction fine-tuning to really find what data sets work, what data sets do not work, and why. And in the end, we came up with a very good sort of chatbot model, Guanaco, that I will talk about more. But sort of one benchmark is often used is MMLU. And here, this is different LLaMA-sized models, different instruction fine-tuning data sets to follow instructions. And MMLU is a task where there's some instructions that are sort of mixed high school knowledge, professional knowledge, sort of general knowledge, and it asks you to answer some questions in a multiple choice way. And what we see is we try all these different data sets, and we see that FLAN version 2 is a really good data set for MMLU. It does much, much better than all the other data sets. It's a much larger data set, so it's much more samples. And if you look at the very largest LLaMA model, it's actually the only model that doesn't degrade performance. And so this seems to be a really good data set. But what we also do is chatbot evaluation, and there actually the results are very different for the FLAN version 2 data set. Chatbot evaluation is very difficult. It's still a research problem, and it's not quite clear how to do it well. Just to sort of give you an example of the difficulty, it's very easy to say if a chatbot model is correct if you have multiple choice answers and you know there's a correct answer there. But how do you evaluate a chatbot model if the prompt is, what are 10 tips that make me more productive? It's a very open-ended questions. There are many more tips. You can come up with more than 10 things. You can also come up with things that are not really correct, but you don't know if they're correct or not. You can come up with different formats. Maybe you have an argument structure where tips build on each other, why it makes you more productive. Or you have bullet points that are much easier to read. And so the question is, which output is better? It's very difficult to answer. And so what we find is that one particular setup is important both for humans and for language models. It's very difficult if you say like, here's a prompt, here's the output, please rate the output from 1 to 10. What is easier is if you compare outputs, because then you have a reference. You can say like, oh, this output has this output has that, and that's why the left one or the first one is better. And so we use the setup both for humans and for GPT-4. And so the setup, we compare the output from ChatGPT versus all kinds of different models and see like how often does ChatGPT win if the winner is judged by GPT-4 or humans. And then what we also do is we have a tournament set up where actually each chatbot fights against each other chatbot. And then either humans or GPT-4 evaluates which is the winner. And if you have this tournament set up, you can use an ELO score, which is a score of skill in a tournament, and which basically goes up if you win against opponents, particularly if you win against strong opponents, and it goes down if you lose. And so over time, the ELO score will sort of form a leaderboard where the models with the highest ELO score are the best. And so we use these two setups. We use the Vicuña dataset, a dataset of 80 prompts. That being said, a big problem in evaluation is to the breadth. 80 prompts are not enough to give you a robust evaluation which chatbot is better than another. It's also often leaving out very difficult prompts that require reasoning or very sort of complex knowledge, very sort of deep expert knowledge. And so while we say our model is like 90-70% as good as ChatGPT, it means it's only as good as that on the Vicuña prompts. Doesn't mean that it's in general that good. But with that being said, let me guide you through some of the results. These are a lot of results, but let me highlight a couple of things. The first thing is if you look at the FLAN v2 dataset on the left. So on the left, it's the comparison just with ChatGPT. On the right, it's tournament, where each model plays against each other model. And so on the left, you see FLAN version 2 is actually a really bad data set for chatbots. And it's not very good if you want to have a chatbot experience. It's good if you care about MMOU, which is sort of a little bit more educational knowledge and knowledge in general. But it's not good if you want to have more general tips that are relevant sort of in everyday life. And so FLAN version 2 does really bad. And that shows you that and you need to align your fine-tuning data with the thing that you care about. But then the important thing is also you need to have the right benchmark to evaluate what you care about. The other thing is FLAN version 2 is a very large data set, 1 million data points. And so if you look at sort of the Guanaco model, which was trained on open assistant, it does really, really well on this benchmark, but it only has 9,000 samples. So it's much, much, much smaller than FLAN version 2, but it performs much better on chatbots. that highlights that, for one, you need to be aligned to your task with your data set, but two, a high quality data set is very, very important. You don't need as many samples, but the quality of your samples are really important. And that's an important takeaway from this table. The other thing that we see is Guanaco performs, if you control for the memory footprint, by far, it's by far the best model compared to other models. If we look at the right, it can even sort of in a tournament style beat ChatGPT on these Vicuña prompts. And so it's a very powerful model. This is also a very small model. This also becomes clear if we look at sort of more recent benchmarks. This is a benchmark, the LLM Sys leaderboard. And this is, the models get all kind of prompts, so it's much more diverse. And it basically ranks models also in a sort of a tournament style arena. And there things are again sort of evaluated in terms of ELO, just to make it a little sort of interpretation a little bit easier. 100 ELO points are about a 15% difference. So if a model is 100 points better, then that means this model wins 2 out of 3 games against another model. Here we see that the Guanaco 33 billion model is pretty good. But the thing is, it's 4 times smaller in terms of memory footprint than other models. So it's very efficient. It gives very good performance for its memory footprint. Here on this leaderboard, the 65 billion model is not evaluated, but it's extremely powerful. You can actually try it online, chat.petals.ml. There you can try it in a Petals globally distributed inference framework. So the model is globally distributed and you basically do inference on this framework. And the 33 billion model, you can Google TGI, Guanaco, Playground. There you find the Hugging Face interface where you can try the model. There you can see for yourself what the difference is between 33 billion and 65 billion. That is, I think, a very important point for QLoRA. It's like a friend of mine says, if you use QLoRA and a very large model, 65 billion, and compare to like a 13 billion model, you just get very new behavior with the 65 billion models. If you want to fine tune a model for a certain task, it's so much easier with a very large model. So the performance is just much, much better if you have these large models, and QLoRA enables that. And yeah, that is the talk that I have. To conclude, so I showed with QLoRA, we can reduce the memory footprint of fine-tuning by a factor of 17. This allows you to train the largest open source models that sort of have very strong performance. Also, the LLaMA 2 models that were released yesterday, easily on one small low-grade data center GPU or 2 consumer GPUs. You can fine-tune a 33 billion model on a single consumer GPU. And we enable this, and we basically replicate 16-bit performance, which is enabled by this new data type, the normal float. And we reduce the memory footprint and out-of-memory errors by using double quantization, the page optimizers. So a very efficient technique. Also yields 16-bit for fine-tuning performance. And recently also added 4-bit inference kernels to the bits and bytes library. So now actually inference can be up to 4 times faster. So if you have a 4090, for example, it's 4 times faster than 16-bit inference. So these give you very fast inference speed. For example, the 65 billion models, you can get 8 tokens per second without any problem if you run it in 4 bits. So very powerful and very accessible. Yeah, and so this is the talk. I will go sort of further into this direction of making models more accessible. And yeah, I think it's sort of very valuable. The more people can use these models, the more we can explore these models and also make progress just building very effective large language model systems. And now I'm happy to take questions. Thank you so much.
Thanks a lot, Tim. That was a very interesting talk. So just a reminder for the audience, if you have asked your question in the Q&A tool and would like to ask the question, like speak the question out yourself, please raise your hand and we'll unmute you. I'll leave you to Neil for the Q&A session.
Sounds good. Thanks again, Tim, for the wonderful talk. That was absolutely fascinating. Maybe just to start out with some questions from the Q&A pool that we have. Towards the beginning of the talk, you mentioned method SPQR, and some folks were interested in just hearing a little bit more about the background of that.
Yeah, so if I go back to the K-bit inference scaling laws, there are a couple of insights. But there was sort of this plot where 3-bit doesn't work really well. What we found is that this degradation is in one part due to outliers in the quantization. So some values, some weights are really important. And so if you extract outliers, you can actually do much better. And so in SPQR, we use, and the other thing that I said is 4-bit is optimal if you just quantize the weights. But you also if you take into account the information about both the inputs and the weights. So how does the error change if the inputs change as you quantize the weights? If you combine these two things, so input-dependent quantization and outlier-dependent quantization, you get SPQR. And so in SPQR, it's a very efficient technique where we can go to 3.35 bits per parameter. And that's currently the most efficient sort of technique. If you want to replicate full 16-bit performance, we just need 4.5 bits. And yeah, that's SPQR.
Awesome, thanks. And someone else had a question regarding double quantization. Is there any reason why we couldn't go to triple quantization, or what's the stopping point at doing something like this?
Yeah, so theoretically, we can go to triple quantization. I think that's possible. I think that there are multiple ways how you can think of it. At some point, they're diminishing returns. You don't save so many bits anymore. So if we quantize again, in this case, we would be at like 0.03 bits that we save. And so at some point, you save just a couple of 100 megabytes, even for a very, very large model. And it's just not worth it because there's a little bit of overhead, there's sort of complexity. The other way to think about it is if you do a double quantization in 8-bit, or let's say a triple quantization in 8-bit, that's equivalent footprint to a double quantization in 4-bit. So if you halve the bits, that's like another level of quantization. And so it feels like double quantization is good, sort of a good trade-off between diminishing returns. And if you actually lower the number of bits in your double quantization, then that is also very efficient and it's sort of sufficient. And triple quantization is not much worth it.
Interesting, thanks. And some folks had some questions regarding whether you're going to try and release a new version of Guanaco based on the recent LLaMA 2 release yesterday. And I guess it would be interesting more generally if you have any thoughts based on some of the more recent releases over the past few weeks and future directions.
Yes. So if I look at open source data sets, so we evaluated like these data sets mostly. These are now already pretty old. It's like things are moving very fast. So there are some data sets that are already much better than the Open Assistant data set. So what we would probably do, and that's something that we planned actually to do, is currently the best data set seems to be Open Orca. And that has sort of a new way of generating instruction fine-tuning data. We would use Open Orca, fine-tune it on the 70 billion LLaMA 2 model. And that's what we could release. That's what you could be able to run on sort of a small rate data center GPU or 2 consumer GPUs. And yeah, we would release that. That would be not sort of the Guanaco trained on the Open Assistant data set, but would be a 4-bit fine-tuned model on basically the best instruction data set that is currently out there.
Awesome. I know and during your talk, you mentioned for neural networks, we really care about the outlier weights. We don't just want to ignore them. And part of the really interesting technical novelty here is being able to account for those outlier weights. I'm curious, in studying a bunch of different models, did you notice that certain models had more outlier weights than others, or how did this change across different families of models?
Yeah, there's sort of a couple of observations. So one observation is that some models sort of are poorly trained in a sense that the standard deviation of the hidden state increases with depth, and that also increases the standard deviation of the weights. There's actually a strong correlation. And so if you take the average over all weights, then most weights are still small, but if you have this effect, some weights get very large. And so that is basically a statistical problem, but it increases the outliers. And you find that, for example, in OPT models, particularly OPT 66 billion, has a very large standard deviation in later layers in the hidden state that causes outliers. Now, there are sort of other models that have very few outliers, and that might also be sort of related to some techniques of controlling the hidden dimensions. One thing that we noted, if you use LLaMA, so LLaMA positional encodings, then the positional encoding for some attention heads is more constrained to sort of not be as long range as typical attention can go. And if you use that, you introduce sort of input dependent addition to the hidden state. And that seems to reduce the number of outliers that you have. So if you use LLaMA, it seems that there are less outliers. Those are the things that we observed. There's some other things. There's a paper by Cohere. If you train in a certain way, you can reduce outliers. We have another paper that's for clip models. If you use something that's not used in natural language processing, but in computer vision, that is layer scale, where you scale the outputs of a transformer block by a vector that is learned. And then actually you can reduce the size of the hidden states, and with that also the size of the outliers and weights. And with this, you can get a bit more control. So lots of different factors. There's more than I already said out there. It's a complex topic. But I think the more we understand it, the more we can sort of train and fine tune in inference and low precision.
That's really interesting. So speaking of training, Sandeep wanted to know, we've talked a lot about efficient methods for fine tuning, but how much of this do you think could be applied for pre-training?
Yeah, so pre-training can be quite difficult. So 8-bit pre-training, just to give a little bit of background, I did work both in int8 and floating point 8 pre-training. And so what I can say, int8 pre-training is pretty difficult. If you have the right setup, you can make it work, but it's difficult to make it efficient. If you have floating point 8 pre-training, that's much more feasible because the data type is better. So you have much less problems and you can actually get good performance. The new hardware, the Hopper and Ada GPUs, they're actually so good with floating point 8 that I think it will become standard in a couple of months. I also plan to sort of integrate 8-bit training, 8-bit floating point training in bits and bytes. But now if you go to 4-bit, all these problems increase. You also have the problem that there's no strong hardware support for 4-bit matrix multiplication. This is not a big problem for inference, but if you have training kernels, it's actually very difficult to write strong CUDA kernels for 4-bit that are not supported by hardware. So the best that you can do is have int4 tensor cores, but we know if int8 is already very unstable, int4 is almost impossible. Floating point 4 might be better, but the hardware doesn't exist. So we cannot do that. So for one, it's a very difficult problem. For two, we don't have the hardware that actually gives you good speedups. So there's not a big incentive to work on that at the moment. I think we will eventually get there, but it will take time.
Interesting. A few folks have asked questions about the interaction between quantization and either learning over time, fine-tuning over time, or various forms of catastrophic forgetting. That come across in your work, or do you know other works that have explored that?
Yeah, so it was very surprising. So let me see if I have a good chart here. I think so maybe if I just look at this table, so these tables are fine-tuned for bit models. And so we take the LLaMA model, quantize it, and then fine-tune. And so what we find this very interesting effect that if you quantize the LLaMA model, then evaluate it just after that, performance drops actually quite a bit. But now if you fine-tune, you can recover almost the entire performance. And we also show that if you do not do any quantization, you fine-tune, the performance is similar. And so this means that it seems that basically no information is lost during the quantization. It can be recovered through fine-tuning after the quantization. And how to think about it a little bit, if you sort of think about a picture and you remove a couple of pixels, you can still see everything. And during the fine-tuning process, the pixels are filled in. And the pixels are so obvious what the right value is that the fine-tuning can fill in the noise introduced during the quantization. So it seems there's very little forgetting, and you can just recover the performance through fine-tuning. And so that makes actually this fine-tuning with QLoRA also, it might make it possible to go much lower in bits because you can recover the error. And so that's a very interesting sort of thought and direction.
Interesting. So Sam in the Q&A first wanted to congratulate you on adding 4-bit kernels to bits and bytes, and then had a question regarding whether 4-bit inference is now faster than 8-bit inference.
Yes, so there are a couple of factors. So for one is the batch size. So right now I only implement 4-bit inference for a batch size of 1. That means a token at a time for a single sequence. So it's still slow for like a larger batch size. But the other thing, if you look at what makes inference fast or slow, is if you have a small batch size, almost all the time spent doing inference is spent loading the weight matrices. And that's just basically where the K-bit inference scaling laws come in, is that the entire time is just determined by how many bits you have in the total model. And this means that 4-bit with a small batch size is just twice as fast as 8-bit. But it also depends on the implementations. For example, in bits and bytes, my implementations are mostly training implementations. They were designed for training, even though the paper that I wrote was about inference. The implementations are for training. And so these are actually not very fast for inference. So you don't get the 2 times faster than 16-bit. And so right now, 4-bit is much, much faster than 8-bit for inference, in bits and bytes at least. But theoretically, it should be a 2 times speed up step function. So if you go from 16 to 8, 2 times. If you go from 84 to 4, 2 times speed up.
Interesting. And a few folks had questions regarding how much of the QLoRA work is NVIDIA specific, or whether it works on Apple Silicon or other accelerators, or if there are any other particular hardware considerations you think are important to mention.
Yes, so there's a lot of new hardware here and there, but all hardware depends on physical laws, and you cannot change these. And sort of, if we have common computer architecture, so basically all chips, they need to load memory. If you need to load memory, that's the bottleneck for inference. If you have the sort of this token by tokens inference with the small batch size, that means the bottlenecks are all the same on all hardware. The implementations that you can use are basically very similar. It's just different code. And so you would see similar speedups on Apple Silicon, on the CPU, on the GPU, on AMD GPUs. The numbers should be all the same. You need to implement it so it's efficient. And that's a little bit different for each hardware architecture. But the overall numbers that you should see is basically what I said. If you have a good implementation, 8-bit is 2 times faster than 16-bit, 4-bit is 2 times faster than 8-bit. That's what you should see on any hardware.
So it seems like one of the most interesting findings from the paper was this sort of variation across instruction data sets, and the extent to which it seems there's a notion of quality in instruction data sets that manifests very strongly. And I know for a bunch of domains folks are looking at curating their own instruction data sets or creating their own. And I'm curious if from this project, you have any intuitions or observations about what you think generally makes a good instruction data set, or maybe qualitative ways of distinguishing some of these data sets from each other?
Yes, so instruction fine-tuning data sets have evolved very quickly. And I think a good example is LLaMA 2. It's basically using reinforcement learning from human feedback, and that seems to be better than supervised fine-tuning, but the data is not good. The open source community already generates data which is better than the LLaMA 2 data set. And so that shows just how quickly things are moving. And so what I would recommend is, it seems the state of the art, as I said before, is open Orca. And so this data set, what it uses is a couple of principles. One principle is you use good chatbot models like GPT-4 or GPT-3.5 to generate prompts and sort of answers to these prompts. But then is two things is you have sort of an evolution of prompts where you try to make them more and more difficult or more diverse, and sort of you broaden or deepen certain prompts. And they show pretty convincing data that the more difficult prompts you have, the better does the instruction fine-tuning model do. And so if you think, for example, you have an instruction fine-tuning data set, it has like, what is 2 + 2? What is 3 + 3? What is 4 + 4? It's not very interesting, and the language model will not learn much from that. But if you have complicated math questions, it made me understand more what math is all about, what people care about in sort of math. And if you can automate this process, you just get very diverse and very high quality data. And so that is important, not how many samples you have, but the quality. The quality is determined both by the breadth and the depth of the questions. And depth can mean how complicated they are, and breadth like just many different diverse topics and sort of reasoning types and so forth. And so all these combination makes a good data set. And I recommend the Open Orca. It seems to be currently the best. There are a couple of others that you should look for inspiration. But yeah, it's good to stay up to date. Things move very fast. Open Orca might be outdated in a week or two.
That's fascinating. I know one question is, you have this wonderful chart where the models just seem getting larger and larger in what you're able to do. And I think someone in the Q&A had a comment of whether any of these methods could be extended to LLaMA 2, which is 70 billion parameters. But more generally, how large do you think you can go? Can you get to 130 billion, or what are your thoughts here?
Yeah, so that's sort of a good question. So these methods work without any problem with LLaMA 2. Somebody yesterday already posted on Twitter like, hey, I'm fine-tuning a 65 billion LLaMA 2 model with QLoRA. It fits on one GPU. So it fits on one GPU, no problem. And the question is like, how far can you go? And then it's sort of a question, what is your GPU setup? What I'm most sort of passionate about is supporting common people with consumer hardware. And there sort of, it seems the 2 GPU setup is relatively attainable. If you, GPUs are pretty big right now, you can maybe sort of force in 3 GPUs on a setup. But if you have that setup, then your limit is about 80 billion parameters right now. If you go to 3 bits, then that increases. I mean, there's some other sort of memory overhead that you have that goes to like about 120 billion parameters on a consumer setup. And there's some couple of other techniques that I'm developing right now, and that allows you to go through with like between 160 and 180 billion parameters. So I think in about 2 to 3 months, that is sort of the limit, 180 billion parameters on a consumer setup.
Interesting. And maybe as a final question, what do you think the future of sort of model-based evaluation is? We're seeing a lot more models at the quality of GPT-4. Are we going to have sort of, for instance, Claude-based evaluation or other types of approaches here?
Yeah. So I think there are a couple of things. For one, if you look at valuation, look at these MMOU scores. They say like plan 2 is very good. And then this benchmark says plan is the worst data set by far. So one is like, what is just your evaluation data set? The other is what is your evaluation setup? this setup that we run with sort of the pairwise comparison is not perfect, but it's a pretty good match. And so with that, you can use models like GPT-4 and sort of you can see as like human annotation as a ground truth. But the truth is humans are very noisy. GPT-4 is more reliable to give you sort of a good ranking between models. So you want to use model-based evaluation, probably in a pairwise setup, to compare your models. Your evaluation data set is very, very important. It needs to be hand designed for what you care about. But if you have a setup, it's still very expensive. I think the move forward is that you get a data set of lots and lots of labeling of GPT-4 or a very good data model. And then you distill with sort of reinforcement learning style value function. You try basically to learn a model that replicates the evaluation of GPT-4, and then you open source that. And so if you have that, it's much easier to quickly evaluate the prompts and get sort of a proxy of what GPT-4 would evaluate this prompt as. And if you have that, you can move more quickly. And so at this point, I think the most difficult thing is to really design a good data set. Or that will become the problem right now. GPT-4 is still a bit expensive, but if we have these value functions for GPT-4 evaluation, then it really becomes just about the data set. And I think we will get there very soon. And then it becomes sort of it can almost become subjective that we need to develop good measures of how to evaluate in terms of data sets. But I think the evaluation method gets more and more robust.
Awesome. Thank you.
All right. Thanks a lot, guys. Thanks, Tim and Neil, for the great talk and the amazing discussion. Thanks to everyone in the audience for contributing with lots of nice questions. Just before we wrap up, a reminder that there's going to be another talk a bit earlier than usual, so keep an eye on our communication channels. And also the talk has been recorded and will be uploaded to our YouTube channel, so follow us there. Thanks again to Tim and Neil, and see you soon in the next meetup. Take care.
Thank you so much.